This conference will now be recorded.
Hello, everyone. Welcome. It's 8 o'clock Mountain, 10 o'clock Eastern, 1500 UTC. Time to start the closing plenary of our 117th OGC member meeting. Today we have a packed agenda, as always. What a surprise after a busy week that we've had. But today we also have a special guest joining us for our opening keynote. So without further ado, let me just remind you, please do record your attendance. Those of you that are voting members, we really need you to record your attendance because we have a lot of votes to deal with today. Go to the technical committee project, pull down for the 2012, it's 2012 TC closing plenary, and add yourself to the attendance, and Greg will be providing a link for you in the chat. Today, I'm very pleased to kick off our member meetings closing plenary with our special guest, Captain Stephen Bowen, a NASA astronaut, captain of the U.S. Navy, who's going to present today on his experience. We all have spent a huge part of our careers looking at the Earth through artificial eyes placed on satellites. Well, now we get to talk with someone who's actually seen them with his own eyes. That's fantastic. Captain Bowen was the first submarine officer ever to be selected as an astronaut by NASA, and is a veteran of 3 space activities, 3 space shuttles, 3 different shuttles, incidentally, I noticed in the more detailed bio, which is quite interesting and maybe leads to one of my first questions if I get to ask. And all 3 of those involving assembly of the International Space Station. He has logged more than 40 days in space, including more than 47 hours in spacewalks, which seems like a lot of time to be suspended out there on a little tether. So without further ado, I'm going to turn over presenter rights to Captain Bowen and let him talk to you about his amazing experiences. So, Captain Bowen, you should have presenter rights. I'll turn off my video so you people don't see me.
All right, well, I assume I'm up. Where is it? This entire screen here. Let's see. Share entire. Okay. I have no idea if y'all can see me right now.
We see you, but not the slides yet.
All right, the slides are coming up right now.
Okay.
Share my screen. Let's figure if I can figure out how to do this. It worked in rehearsals. Isn't that the old Timex ad? With
yeah, it is.
So, you know, we get to choose a bit as to what we, when opportunities come up to do public appearances, and this one came up, and I looked at it and I said, this would be an interesting group of people to speak with, because just the concept of being able to standardize and synchronize and make it available to the world, all of the location information, all of the spatial information is incredible. And it really sort of relates to challenges I've met throughout my career, but particularly we'll talk at the end here about some of the things that have happened more recently, like actually in the past few weeks. So anyway, this is me. I'm Steve Bowen. This was a day at work on STS-132.
Oh, we still don't have your slides, though.
Oh, yeah. Let's try this again. Share my screen. Yes. Share. Entire screen. Let's do application window. This one here. Share.
Oh, maybe.
Is that better?
No. And it did work perfect for me. So, oh, wait, here we go. Yes. Fantastic.
All right.
Thanks.
So this is the problem, right? This is the technology issue that you guys have to solve, which is how to make information, how to make data available to everyone when they need it. So there's an example of problems that we have going forward. So I grew up in Massachusetts. I grew up on the water, about 3 or 4 miles from the beach. I went to the Naval Academy where I initially wanted to be a pilot, but over time I ended up joining the submarine force, which was a fantastic place for me. After 14 years in the submarine force, I had the opportunity to apply to become an astronaut, and I applied, and it can't remember how many. I think we had 8,000, 9,000 applications the year I applied. We chose 17. More recently, we had 18,000 applicants the last go round. The current, I'm not sure what the numbers are this time around, but out of 18,000, they chose 10. So it's sort of a roll of the dice, luck of the draw, and you feel very fortunate to be selected to be an astronaut. There's no expectation you ever would become one. But like I said, for 14 years, I was in the submarine force, and understanding where you are in a submarine. So we relied a lot on IMUs. I went from these big giant gyros, the SINS system, if anybody's familiar with that acronym, through ESGN, and I always used to take the submarine, try and get to periscope depth from whatever operating depth we were at as quickly as you could, so you could pick up NavSats as they came across the horizon, because you wanted to minimize your time at the up at periscope depth, and you got very proficient in that. But of course, that changed, and suddenly we had GPS available to us, sort of in the early mid 90s, when we started getting all the boats fitted with that, and suddenly you didn't have to rush to the surface to get that information, so you could have a better understanding of where you were and how things sort of best. And so, like I said, I went from big gyros, and the latest, when I was leaving the boats, we were down to RLG, ring laser gyro systems, which are plentiful and available today, so people know where they are on an inertial basis, for starting from a fixed point. It's just funny thinking back over 30 years, and there were times underwater, where our best understanding of where we were over any extended period of time was essentially hand DR. You would look at the speed you've been going for an hour based on the logs. You'd kind of adjust based on the current as you understood it for where you were in the world, and you'd put a point down on the paper, and you drive like that for extended periods of time. You'd go back up to periscope depth, and like I said, we pick up a NavSat and or an Omega or Loran or any of these other navigation systems to help fix our position, and we'd bring that big circle back down to a much smaller circle, but it is nowhere near where we are today in our understanding of how we are and where we are on the world. It's pretty amazing to think about where we came from. So as I said, I was selected to become an astronaut in 2000. My first mission was STS-126 in 2008, and this is the crew of STS-126. You can see Shane Kimbrough there on the right, in between Heidi and Eric, and Shane is heading to space here in a few months, and I know there's a classmate of his in the audience, so I just kind of point that out. So any jokes I make at the Army's expense, I've earned that right to mock them as much as I possibly can in this week we have going ahead. We also, this gives you a good example of the diversity of the crew. On the left, we have Sandy Magnus, civilian engineer, just an amazing scientist. We were taking her to space station for her first increment flight in 2008. Then there was me, then there's Don Pettit. If you ever get a chance to see any videos online of Don, he does a really good job sort of explaining science and how it relates to space flight, and he does experiments, and he's very entertaining. He's probably one of the smartest human beings I've ever met. Chris Ferguson was our commander. He commanded the very last space shuttle mission. He also was the lead for Boeing's commercial crew program. And then I mentioned Eric Bowe. Eric was, actually I was on 2 flights with Eric, Air Force fighter pilot. Pretty amazing person overall. He's currently our liaison with SpaceX out in LA. And then Heidi Stephenson Piper on the far right. She actually went back to the Navy after our flight, retired as a Navy captain after leading a maintenance facility in San Diego and a testing facility, Carter Rock there in DC. She was our lead spacewalker. She's taught me everything I knew about spacewalking, and it was a great experience to work with her. So I flew 126. I flew again, STS-132. STS-132, you'll see this group again because it's another diverse group of people. But this flight was the first flight in almost 10 years where everybody on the crew had flown in space before. And that taught us some things we tried to highlight during our mission, and I'll get back to that in a minute. My last flight so far was STS-133. So STS-133, when I talk to students, and students is usually the audience we end up speaking with mostly, I always ask the students if there are classes they take that they don't like and how they should study, and then what do you do with that information after you take that test, that final exam? And more often than not, somebody says, you dump it, you forget it, you get rid of that information. And so when I came back after STS-132, all of the flights had been assigned through 133, 134, 135, and there were no flight assignments left. So some of my crew actually left the office. I doubled down on my Russian training and went back to all the ISS space station systems I'd worked on for years, waiting for my opportunity to fly to space station. Fortunately, I did not dump all the shuttle information because the lead spacewalker on STS-133 was injured in a bicycle accident, and I was called in to replace him 6 weeks before launch. So fortunately, because I had not dumped all that information, I had the opportunity to fly in space, and we had a successful STS-133, the last flight, Space Shuttle Discovery, and it was a great flight, and it was a great crew to jump in with. Everybody else, except for the commander, Steve Lindsay, in the middle, had been a classmate of mine in my original astronaut class. But as I said, my flights in space so far. So I was training for a increment mission on a Soyuz launch, and this is the crew I trained with for almost a year and a half to 2 years, Anatoly Ivanishin and Ivan Wagner. And due to an injury in the crew ahead of us, the crew I ended up training with for the last month before we were the backup crew was totally different. So the crew I was training with for almost 2 years, 18 months, suddenly became the prime crew to fly to space with Chris Cassidy last year. And we picked up this pickup crew here, Andrei Babkin and Sergei Rizikov, and we put together and we successfully completed a backup flow. Unfortunately, we kind of fell apart after that. The requirements when I came back during the COVID era, I should say, and our mission requirements shifted, and so I did not get my Soyuz flight, but the opportunity to train and learn and fly and understand how the Russian space program, how the Soyuz system, the engineering of it worked was fantastic. I did, however, fly 3 times on the space shuttle. This is from one of my flights, STS-126. In the payload bay, we have the MPLM, which was a resupply system we had, which has basically been replaced by both Northrop Grumman's system and SpaceX for resupplying space station. We currently have both of those vehicles attached to space station right now. I did do 7 spacewalks, almost 48 hours outside doing construction work. I joke, I grew up in a house. My dad laid tile for a living. So I've got a brother that's a house painter and another brother that lays tile. And so I often joke that they hired me because it was cheaper to hire me than to contract out and hire my brothers to do the maintenance work on the outside of space station. But it's just a remarkable opportunity to go out and work on the space station. Is the most complex machine mankind has ever built, 220 miles above the Earth, continuously circling every 90 minutes. It's a remarkable scientific laboratory that I don't think we'll fully comprehend the impact it has for generations. It's been operating for 20 years, which means over a third of the world's population, as long as they've been alive, people have been continuously living in space. And that is absolutely amazing. I don't think we've grasped that. We are no longer tied completely to the surface of the Earth. And in order to do that, as I said, one of my crews was the first time in 10 years that everybody had flown in space before. And the one thing we all understood, we said from day one, Flying in space is like so many other things. It's a team sport. You may see the astronaut doing the sort of the, as they call it, the pointy end of the spear, but there is an incredible team behind them putting it all together. We actually, Ken Ham, the commander of STS-132, actually called up the Astros and borrowed the stadium there for a day so we could get this picture. Mostly that's our flight control team and our trainers who came out on a very cold day. We may have been the only people that were comfortably warm to be in the picture, to be part of that team, the visual part of it. Because often you see mission control and you understand that those are where the decisions are finally made. The flight director takes in the information, passes it to the Capcom. Capcom communicates to the vehicle in space, whether it be space station or a shuttle, or Russians do it the same way on a Soyuz. It's a big team. What you don't see necessarily is in the back rooms when there's 10, 15 people working continuously, monitoring all the data and all the systems and all the procedures to make sure things are getting done absolutely right to ensure that we safely operate and exploit our research opportunities to get as much as we can out of our time in space, really to make life better here on Earth. It is a remarkable facility. And it is, as I said, circling the Earth. You all are spread out throughout the country and probably overseas as well. And you should check online, and whenever you get the opportunity, go outside and take a look at that bright light, that bright star as it moves across the horizon, from the horizon up into the overhead and back down to the horizon sometimes. Just incredible. Think about it. Right now, we have 7 people living in space, which is amazing in and of itself. But at the same time, they're doing research and really exploring space, how to operate in space, how humans live in space, but really how basic research, our understanding, how do things react without that gravity vector? What is different in a vacuum? We can maintain those science and research facilities and just enhance our understanding of the world around us. It's a great facility. It's going to be operating for more than another 10 years, I hope. It's just a great thing. But, we're moving on. And so Space Shuttle retired 9 years ago, I guess. And we went into the commercial crew era. Only this past summer did we get our first commercial crew vehicle to come up and dock to the space station. And that is a giant leap. It really is. The commercial industry, the commercial space industry is just growing, and our understanding of it, of what we can do when you have access to space. Obviously, microsatellites, the CubeSats, the abilities to deploy real-time satellites for commercial systems obviously impacts everything you all do with the data they receive and what understanding they bring to the Earth, but also the opportunity to take human beings to space. There will be those that go as tourists, and they'll bring back their stories, and that will help expand the industry. But ultimately, there'll be manufacturing. There's things that are probably easier to build and create in space. There'll be more research, more private research, and all that is just starting out, and it's just amazing to see. So this is an image of the Dragon vehicle this summer arriving at the International Space Station. We've had another one dock. We've got pretty recently, we've got a crew on board right now from the second Dragon flight. Boeing hopefully will fly in the next year, and we'll have 2 competing systems for getting human beings to low Earth orbit. But really what this allowed NASA to do was look beyond low Earth orbit. We generated a lot of tremendous science. We've learned an incredible amount of engineering, and it really is our time to go back beyond low Earth orbit and continue to explore and really maintain and create a lasting impact for what we're going to do in space. So the first crewed flight of Orion won't go to the moon. It's going to go and circle the moon. And so this is probably about 2 years out, based 2.5 years out, based on our current plan. So we'll have a crew that will launch, get into low Earth orbit, do another burn, and then head out beyond the moon, which will be the furthest. Actually, I think the free return maneuver actually sends them further than any other crew, any of the Apollo crew from Earth that we've ever been. But this is really just the first step in exploring the moon initially, and then moving deeper into space. So for years, as new missions have come, we've tried to work and understand what it would take to execute that mission. Several years ago, we were going to go to an asteroid, and we actually developed, using our existing suits, our existing pressure suits, not our exploration EMU, our extravehicular mobility units that we use for normal spacewalks. We're actually going to use the pressure suits we launch and land in, and enhance them to allow us to research and try and do an EVA on an asteroid. But obviously those missions evolve. So today we're looking at the moon, and we've got in the middle there, you see a current EVA, a spacewalk using our EMU. On the left, you can see, I think it's Laura O'Hara. She's in a next generation spacesuit. It's not technically the XEMU. It's a Z 2.0 is what we call it, and it's an evolved spacesuit that's really built to operate on the surface of a planet. In the configuration that we've developed at this point, it'll work well on the moon because there's a vacuum there, and so our environmental control and our life support systems will work well. But the mobility of the suit, she got out of the water that day, and she could just use that suit all the time because it was just an incredible amount of mobility relative to what we've been working with for the EMU, which was designed to operate in space. But that brings different challenges. If you look to the right, there's the image of some testing and training and development that we're doing for lunar exploration. And the moon is a different place. I know some of us are old enough to remember the Apollo missions and distinctly remember some important things as far as, when Neil Armstrong landed, he only had a fuel left because they had to change from their landing site based on the boulders and the rocks and the field that they initially thought they were going to land in. They had to reposition. And that's a big issue. We had I think it was Apollo 17 that had significant slope they landed on. And so if you ever see pictures, the lunar module looks like it's significantly tilted. And all of this goes back to things that you all work on in this organization, that understanding of the geospatial environment. In this case, it's the moon. So I'm going to run this video, and this is actually from the Chinese probe that landed on the moon and retrieved a sample from just a couple weeks ago. And when this first came out, we ran it around the group. The group I work in, I'm the lead for spacewalking, lead for EVAs in the astronaut office, but I also work on exploration. And so on the exploration side of things, when we looked at this video, we had a lot of chatter. We can't actually be in the same room because of the restrictions we've got on right now. But it was pretty clear. Everybody came up with the same understanding of the problem that we face. And I'm going to run this, and then we'll talk about this, and I'm sure you might end up with some questions at the end. So this is the Chinese probe coming to land on the moon. And this video is just absolutely amazing, but it highlights a huge problem. So you can see the landing legs, the shadow of the landing legs there of the probe as it gets down on the moon. One of the thing that struck us the most was the fact that no matter how far away you were, what altitude you were, almost independent of angle of incidence, once the horizon was out of view, you had no gauge as to measure what your altitude was, no matter how high you were. So this is the field. This is an image of the area used at Johnson Space Center to practice and develop the techniques that we will use to explore the moon initially. And so you look at this image, obviously you don't get any relief as to what's flat, what's, you get some cues. There are a couple shadows that might give you some ideas as to how tall things are, how small things are, what's flat, what's not. You may get a sense of the different surfaces we practice in, what we're looking for. But if it wasn't for the tractor there on the left-hand side, your sense of scale would really give you no idea as to relatively how big that field area is that we work on, and that gives you an idea. So this past week, I had the opportunity. We've evolved a little bit since this picture was taken. This is somebody else doing this during the summer, but we actually go out and we have systems that allow us to communicate back to a central post. We're trying to develop the tools and techniques and understand what it will take to really get the most out of every single opportunity we get to explore the surface of a planet, how we will tag, mark, locate, identify, and fully understand the environment that we're going to explore. So I think it was basically at this point the other day when I turned the corner and I went behind this hill. It's a gravel hill, a rock hill, made out of the tailings from probably some of the buildings we've in recent years that needed to be remediated here at JSC. And so they built a hill, and there's some pretty big boulders and stuff built into it. But as soon as you turn the corner and you step behind this, you don't know where you are relative to your vehicle that we landed, our lander, basically. The HLS system, which we're developing with commercial commercial entities right now, which is also exciting. But understanding where you are on the surface is extremely important when you're doing science. And so we're dropping a tag here. We'll take a picture of the tag. Having that ability to navigate, though, is still at a loss. We had this long discussion at one point when the person that was giving us direction said, well, the field, their next point is northeast of the feature you're at now. And my EV2 and I looked at each other and said, and which way is north? Because there is, where we were standing that time of day, it was overcast. It was like, which way is really north right now? And it doesn't help if you don't have that common reference point to mark where you are. For that experiment the other day, for our training the other day, we had a map based on that photo that I showed you earlier, and I would pick a point on the map and I'd give my relative location to the point to allow them an idea where I was or where I thought I was, because at least at one point in time during our discussions, it became clear that I had rotated the map about 90 degrees, and so EV2 and I were talking back and forth, trying to make sure we were giving the right location. And so going to the moon is going to be hard. It's going to be technically hard. It's going to be just an engineering feat that is going to be hopefully repeated over and over again. That's the goal. We want to go, we want to stay, we want to understand, we want to learn as much as we possibly can for our exploration. But a lot of what we learn, we bring back to the Earth and we use here on Earth. I'll digress for a moment. So on space station, on my first mission, we brought up the water recovery system, and I had worked on this system earlier on in my time at NASA. And what it did, it rapidly took waste water, urine, sweat, condensate, and turned it very rapidly into drinking water. This had a centrifugal and filtration system that was able to be efficiently run, because that's always a constraint for flying in space. You got to make things power efficient. And what developed out of that was a very portable, very quick, inexpensive, low power system that today they take to places of the world that don't have any ability to make or get clean water in a timely fashion. And so there are these units that they're able to deploy and get people clean water. So we never would have had that if we hadn't asked the question of, what do we do when the shuttle retires and we can't bring water to the space station anymore? What are they going to do for water? So they came up with a system solving that problem, that specific problem. And by extension, it solves problems back here on Earth. The engineering standards that we use to build the space station, many of those modules never, ever met on Earth. They met in space, they worked, and that is a standardization engineering miracle in my mind. How these different countries building modules in different parts of the world with different tool sets managed to create something that linked together and worked the very first time we brought them in together in space. So thinking about the disparate databases and systems and standards that you all have to bring together to get this location information and geospatial information available for the Earth together is just a computing data management miracle. So it's amazing to see what we can do. And I've been showing this slide for 20 years, and I still find it amazing, because I can't think of a single spacesuit, even the one we're building right now, where I want to be rappelling down the side of a cliff into a valley, although this would be kind of cool to see. So I had to show you at least one of the pictures I took. And the story of this picture is, so my hometown's in here. I grew up in Cohasset, Massachusetts. But the funniest thing about this picture was the fact that it's so bad. We were on STS-132. We had this incredible pass circling the Earth. We had time off. They had given us a couple hours to get organized before landing. And so we started off over New Zealand at night, and just incredible pass up across the Pacific, up through the Gulf of Mexico, across the United States, up over Massachusetts. And we were all taking pictures pretty much continuously. The problem was we had set all our cameras up for New Zealand at night. And so our pictures over the East Coast of the United States in daytime just did not come out as well as they should have. This is always a continuing problem with our using human beings to take images in space. Is, yeah, we can do it, and we can do it well, but we need to be consciously thinking about it. And we have systems in place that actually allow us to do that on space station now that are quite remarkable. They take the data for the space station location and what the visibility will be, where the shadows will be, what the angle of incidence for the camera will be relative to your target, and what it will look like in the cupola, and what cues you will have going in ahead of that. So in just the past 10 years, our ability to do Earth observation from space has improved, even on the manned side of it. The human being taking that picture from the cupola has so many more resources to help them get the good picture, get the good shot. It even recommends settings for the cameras, which would have been helpful. You know, we're heading out of low Earth orbit. We're heading to the moon within the decade. You know, this is just the first step. I often mention Stephen Hawking and one of my heroes here, John Young, who both basically said the same thing. which is single planet species don't survive. And every step we're taking now enhances life here on Earth, and ultimately one day will allow us to leave Earth and move deeper and deeper into space. So that concludes my presentation. Hopefully that wasn't too insufferable. I'll let you all decide that. Let me get myself back to where I was. Piers. End show.
Well, we see you. So
You see me. Okay,
yeah,
good.
that was absolutely fantastic at the Bowen. We really enjoyed that. Lots of great comments in our chat of people just too excited for words. And as you
I can open that up now.
the camera settings, you saw probably 100 people online nodding their heads because cameras. So
we were kicking ourselves because I have while we were on station, I mean, you get a lot of camera training, and it's really a lot of fun, and it's really important. And we all knew we had ourselves so well set up, and we actually had a plan, but we got so excited at what we were doing, we didn't execute the plan that we had. And it's just a great reminder to myself because, looking through the lens, I could pick out streets in Boston as you're flying directly overhead. And when we took the images and we looked at them, we were like, yeah, we know what we did.
Well, do you have time for a few questions?
I do actually. I'll stay as long as you want. I know you all have work to do, but I'm perfectly willing to answer questions. Because the next thing I have to do is change the password on my computer since it's a new computer, and we all know how much fun that is.
Yeah, we'll try to keep you from that task for a little while if we can. Great. So we have quite a few things. I'll start with one that started as a comment that leads to a question. And that is, NASA has this incredible and long history of technology transfer. You think of Velcro as the example everyone uses time and time again. And so incidentally, there's a technology transfer we're using in the OGC right now, and that is NASA's SPICE specification, which describes the three-dimensional position and 3 degrees of orientation of an object in space. And so we're using that in one of our standards now that we're developing as sort of the foundation for the way to describe orientations and such. What do you see as sort of the next big pending technology transfer? What have you seen that shows great promise here on Earth?
That's actually a really interesting. I've been so focused over the past 6-8 months since I ended training on the EMU, and so the new exploration EMU and the systems we've been developing for that. On the life support side, I think I keep thinking of the life support system of the XEMU, and just once that actually we get to see it actually function in space, it works well here on Earth, and it was designed to solve problems with the old EMU as far as water, water purity. But it uses a membrane system, and sublimation is still a part as far as how to keep cool. But I think there's things in there that when people get a chance to look at it and understand it, that we'll be able to exploit for solving additional problems here on Earth. Which I think on a broader scale, it's hard to say. There's just so much going on, and in my little, from my little cubicle to look out, it's hard to say what's there. I'm happy to see the SPICE systems out there for that standard to understand how we can orient in a particular point in space. That's pretty slick. I always find it amazing. So I don't have a good clean answer on that one. That's a good question though. I'll think about it.
All right. Well, you did bring up a great one with the your water treatment systems that we're seeing applicable. So that's fantastic. We have a couple questions that are related. I'll start with the preface where the surveyor landing on the moon in 1966 did not know if the surface would be solid enough to support the craft. And then based on that, what are the biggest unknowns for the future of space exploration? And related to that is maybe the biggest scientific challenges. So big unknowns and big challenges.
Well, I think I showed you some of the unknowns, that scale invariance. As you're approaching the moon, I've seen it in sonar systems, but to really watch that video, and no matter how close you were, you could have been, at almost any altitude. And so the engineering challenge of safely landing on the moon in a flat spot without a huge slope is going to be really difficult. Looking at that technical challenge ahead, understanding where we are when we explore the moon, our ability to accurately mark. If you think of GPS and what that has done to our ability to function and operate here on Earth, every human being, the accuracy of that system, the ability to use relative GPS, and you can bring it inside now and get inside buildings. You can find out where you are, which is absolutely remarkable. But we need to do that on the moon. We need to do that with accuracy enough on the moon that we get a really good understanding of what the geologic history, what the geographic layout of the moon is. How did it get that way? And just changes of a couple feet can change our understanding of how the moon came to be and how that relates to the Earth and what that means for us. So navigation, I think so. Communication, navigation, and lighting right now are the three big problems I see for our initial exploration of the moon. Down the road, I see power as a fourth one. Communication, we just will never have enough bandwidth to get the information we want back to the Earth. We are discussing the bandwidth for video. So the helmet cameras, the cameras we use for doing an EVA are old standard def cameras, but if you add an HD camera on there, your understanding of what you're looking at, where you are, is enhanced by that signal going back to a control center where others can view it, and add information and understanding that you would not have just looking at that field. So our ability to explore really depends on that bandwidth, that communication bandwidth. Lighting, so they're talking about going to a pole, and if we're close to a pole, the angle of incidence of the sun, I think about 2 degrees, 3 degrees at times, that will give you incredibly long shadows and obscure some incredibly important information if we're not smart enough to bring sufficient lighting to help us look at some of those regions in shadow and get a good opportunity to explore and see what we otherwise wouldn't see. That also goes to that scale invariance I was talking of earlier. Those extremely long shadows really will hide. You probably don't want to land in a shadow because you'd have no way of seeing, of looking at it. So there are some really important things. So communication and navigation on the Earth as you get to a pole, and this has always been a problem. So our charts in the good old days never really worked. Once you got above a certain latitude, you had to change actually how you navigated above a certain latitude, because everything is south from the North Pole, right? And if we're at the South Pole of the moon, we will have a similar problem unless we really have laid out that markers and the relative positions and the real method and system for navigating at that part of the moon. You can rotate it, and you can mathematically it's not that hard if you want to do it that way, but we have to come to some standard and have everybody speaking the same language, and those three things I find incredibly important. the navigation thing, I was part of the Columbia recovery post the Columbia accident back in 2003, and I was amazed when I got up and I asked the question as to what standard we were using for our GPS tracking, so that everybody would be talking at least on the same relative scale where things were found and where they were. And because it had started off that first day, it took a couple days for us to pin everybody down and come to a common understanding of what reference we were going to use. Because in the hard piney woods of East Texas, if you're off by a couple yards or 20, 30 yards, you may never find that piece again. So we need to do better than that when we get to the moon. And I think that'll be a really great opportunity to bring everything together and get a really fine navigation system that I'm sure in doing that, we will learn how better to do it here on Earth. So anyway, those are the basic challenges ahead for initially anyway. Power road, and there are solutions to that as well.
Fantastic. That video of the moon you showed was great, because I kept watching thinking, okay, these craters are pretty big. They're pretty big. Wait a second, they're on the ground. Not at all what I expected to see.
Yeah, so actually the group I work with, more than half of them are pilots, including several helicopter pilots. And that was exactly the thing was, I kept thinking we were close, but we weren't.
Well, you're really fortunate today that there's several NASA scientists on this call as well, who've been chatting away on our little chat. So you've probably seen a number of questions and answers, but you talked about navigation. Perhaps if you can speak to, are there even thoughts of someday having something like a GPS on other bodies in space, some sort of constellation of navigational assistance?
I hope so. I think that would be really important. We often talk, well, I won't say we often talk, I guess I talk to people about sort of the rural electrification program, and there was another initiative. Actually, there's an internet initiative trying to get Wi-Fi into cities, which are government-funded projects. And I think of navigation, what resources, what systems could we leave behind for commercial groups that want to go and explore the moon or use the moon? What can we leave them? What infrastructure would be really significant that would have a long-term impact? And I think a navigation system, it may not, I think we can do it differently. I think we've learned so much since the initial GPS satellites went up that we could probably do it differently and much more efficiently and more accurately now for the moon. And the payoff, leaving that infrastructure behind or allowing others to use that infrastructure, when they took the dither off of GPS, suddenly the commercial world opened up. We were able to fly airplanes with such precise navigation that opened up the skies to so much more and so much more safety. And I think of those changes and what that could mean for the moon and ultimately onto Mars. So that would be a key one. That what infrastructure can we leave behind for others? And that would be the question. Navigation is the obvious one to me right now. Communication obviously would be another one. A communication system that would allow continuous communication between the Earth and the moon. And how would you solve that problem? And again, we solved it for the Earth. I am absolutely sure we could do it more efficiently and better for other planetary bodies. I have to throw a caveat in there for anything I get wrong technically. I'll let the NASA scientists in your group correct me as much as they want. I claim no special knowledge.
Thanks. Fantastic. Yeah, and I'm always impressed by how large of an industry already space mining is, despite the fact that we have no miners yet.
I spoke a couple years ago at a group at MIT for, I can't remember what the name of the organization was, but I started off the speech by saying it is so exciting to be in a room full of optimists, because this was the space business in its origins. You know, these are people who were staking their financial future on space exploration and using space, not necessarily for mining or manufacturing, although those groups were there, but even the Earth observation side of it. The microsatellite people, what can we do with a CubeSat? How many CubeSats can we have up there for how long to get this information? And it is incredibly exciting. It's so much fun to watch that group of optimists. You got to be an internal. There were people with business plans that spanned a century. Think about that. This is not the 1970s Harvard Business School of, cut your engineering department once they've done their work and take all the money and run. This is, hey, we're going to sustain this not just for myself, but for the children of my employees. And that is just remarkable. And that change is I'm glad to see it. Hopefully it expands across the entire world.
Yeah, that long view is wonderful.
Yeah.
Thanks for that. Another question, have you ever had data quality problems with the spatial data or other data you've collected or used in space, other than, for instance, not knowing what scale an image was like?
Yeah. In my head, I've been lost outside doing a spacewalk, but I think that was an internal problem. I was still attached to the space station. I just couldn't figure out how to get to the next spot. And we don't have anything that's going to tell me. As a matter of fact, one time there were no cameras where I was at, so they couldn't tell me where I was to start with. So I had to physically describe where I was to ask how to get back to where I needed to be. It gets dark up there. It's pretty cool. Not specifically for any of my missions. We do diligently on the space shuttle. We were very cognizant of the potential for being wrong and the impacts that would have on us. So we had systems on board. You could do the visual check. We would always have world map up so we could see where we were relative to the Earth, and we could look down and verify, hey, yeah, that's actually where we are. Sunrise, sunset were great markers. But the errors that are smaller than that, the ones you wouldn't pick up on, we had star trackers that we could align to ensure that we were where they said we were, and our corrections were almost always extremely small. So our navigation systems, we had high confidence in. Space station is the same way. We have independent systems on both the Russian and USOS, the US segment, that keep our position of the space station extremely tight, extremely well known. And you've seen that. You saw that just this past week when SpaceX 21 autonomously docked with the space station. They launched from Earth, launched from Kennedy last week. They got to orbit, they did their burns, and they showed up where they were relative to where they were supposed to be right on time and docked autonomously to the space station. When you get close, you can do relative navigation, but just to solve that problem, to get there, I still find that absolutely amazing. So no specific problems for me, but it's a continuous worry for everybody in the space business.
Yeah, watching that docking and then watching the flight just a few days ago from SpaceX, it's been since the shuttle days that I've been since I last watched live launches and activities, but I find myself doing it all the time, and maybe that's why I'm not getting as much work done as I should.
It's part of my job. At least that's what I tell myself every time I watch another launch or anything going on in space. I say, yeah, it's got to be part of my job.
Perfect. Well, I have one sort of final question to wrap things up for us that I think is very reflective of what we do here at OGC, and it's, what is your opinion is the biggest challenge in Earth sciences and space sciences can help with here on Earth? So we all look out with the big space telescopes and our land-based telescopes, but what can NASA and the space community do to help us on Earth? What's the biggest thing we can solve?
That's actually probably a question that you get a much better answer from somebody else. But for me, looking at the data that we get from space, this goes to another one of my soapboxes. I still think the greatest impact the Apollo program had on the world was us, our generation, where we became engineers and scientists and doctors inspired by the fact that science was cool. Science was exciting. Was exploration is a motive that doesn't just send more people to space. It made our computer industry, our satellite industry, which changed how we do farming, which changed how we do medicine. It's just, I think bringing that understanding, and I didn't see outreach as part of your mission statement there at the end, but letting people know that they are significant in the sense that they are a part of the Earth, and we have where they are on the Earth, what is happening in their little region, their 10-yard square, or trying to look at my room here. Let's see, I've got 5 meters by about 5 meters. No, yeah, I think that's about right. My little square here, letting people know they're significant and that they are a part of that Earth. The blue marble sort of was the start of that, I think, making people realize that we're all on this planet together. And I think the information and understanding that this organization helps bring together, getting that understanding out is really important. So, there's specific issues that as far as agriculture and geology and geography, that understanding really can be brought out of what you're doing, but getting it down to the individual level, I think, would be really significant. One question off in the chat, the last one there, any anecdote on data preservation difficulties in NASA? And I have to comment on that one. So I was on STS-400, a mission you probably have never heard of. We were the rescue mission for Hubble. So STS-125 launches. It was the last mission not to go to the space station. The Columbia accident had occurred, and so the concern was, how would they be rescued should something go wrong and we have a disabled space shuttle in space? And so they came up with this STS-400. Initially, it was the STS-123 crew. After their flight, there were 4 designated to be the STS-400. After my flight, because there had been a slip in Hubble, STS-126, Shane Kimbrough, myself, Eric Bowen, and Chris Ferguson became the STS-400 crew. So Shane and I went down and we launched STS-125. We were part of the closeout crew down there, flew back to Houston and went into quarantine. We were in quarantine for a week or so, anticipating potentially the need for us to launch. We actually had 2 shuttles on the pad when 125 launched, to launch and go and rescue them. And we had all the flight data file that we had marked up. We had all our markings in there, our personal notes, all written in that data file. When that mission 125 landed, it comes back. Everybody's safe. Everybody's good. We get to disappear into the fog of history or whatever. They were going to throw away our data file. Had no place to keep it. So I called a friend at the time who was running the Kansas Cosmosphere, who actually also owns the Apollo 13 capsule. You might want to look into preservation on that side too. And they took our data file. So NASA, which I think is actually kind of wonderful, we're continuously moving forward, continuously moving ahead. And so it's difficult sometimes to preserve everything. And I'm sure you all run in that because we will have an infinite database of information that you're going to try and manage. And at some point, you can't do that. But once in a while, you kind of have to look and see, well, what is important? What can we save out of this data that people may need to look at in the future? So that's always my example for that. But anyway, so if that's the last question, I want to thank you all very much for allowing me to speak. This was really interesting. I'm sure I could babble on for a while. And just thanks again.
Well, thank you. As you saw in the chat, inspirational was a word that came up really frequently. And this was wonderful. I've had a gigantic grin on my face for an hour, and my actually ears hurt right now from that grin. This was really great. You're getting virtual applause, a go-go here. This is really wonderful. Feel free if you want to hang out and watch all sorts of presentations, but we understand you've got another job to do too. So thanks again, Captain Bowen. It was wonderful.
Thank you very much. Have a great day.
All right, you too. Thank you.